Hello, everybody. My name is Lewis, and I'm a fourth year PhD student at Professor Kallenberg's lab. Today, I'm gonna introduce the notion of post layout checking and extraction. So first, let's take a look at these slides that your TAs have assigned to you, and let's look at this graph for a second. So previously, what we've done were we have the schematic design, we created symbols, we've done some simulation to verify it, and then we have completed the layout in the previous section. But now, after the layout, there are a few checks that we need to do to make sure that our physical design put into layout actually works. So the first thing is on the, surface level, which is DRC and LVS, which stands for Design Rule Checks and layout versus schematic. I'll introduce them one by one afterwards. Once we finish these checkings, we make sure that the layout that we made is not only manufacturable, but also the same and matches with our schematic. We will now proceed to parasitic extraction, also known as PEX. Because of the routing that we made in the layout, there will be parasitic capacitance, resistance, even inductances included in the layout, in the actual layout, compared to your schematic, which has every routing as ideal. So in this case, they will introduce some extra degradation or who knows, improvements in your simulation. And that's why we need to perform this parasitic extraction to extract the layout parasitics. And after that, we can use that extracted view instead of the pure schematic design to run post-layout simulations, which to verify that your layout design, the actual physical design that is going to be manufactured, that is going to be taped out, is performing the way that you want it to be. So in today's video section, we're only going to cover DRC and LVS and how do we do it in Cadence. We're not going to cover parasitic extraction in this section, but it will be covered by Shashank in the next. With that, let me first introduce the notion of DRC. DRC, and again, this is design rule check, is basically to make sure that your design meets the layout rules specified by the manufacturer. So in our case, we have to make sure that everything that we draw in our layout are manufacturable by Skywater. So this example here given shows that if the two transistors that are too close to each other or even overlapping each other, the company, in this case Skywater, they will not manufacture the circuit because this is a flawed one. It does not meet with their manufacturability. That's why running DRC is basically going to tell us is our design, is our layout manufacturable or not. And if it's not manufacturable, it's going to point you to where it is not manufacturable, and you have to fix the problems for a successful tape out. Now, LVS, on the other hand, stands for Layout versus Schematic. And this is a CAD program that runs and extracts the circuit diagram from the layout and compares it with the original schematic. This is to make sure that when you're laying out your actual schematic design, you did not miss anything or you did not make any mistakes. Right? For example, if you have two transistors that are supposed to be connected to each other, but you for some reason forgot to do so during layout, then the layout versus schematic is going to detect that error and it's going to tell you your layout does not match with your schematic and you need to fix it. Technically, you can tape out your chip as long as they satisfy the DRC checks without the LVS checking. But I mean, then you will be taping out a circuit that you didn't design for, which is obviously wrong. So a funny thing, as I have mentioned in the previous video about LVS, is that in LVS checking, it assumes the layout doesn't know schematic at first. It's going to extract the layout and come up with a schematic or netlist from it, and then compare with the netlist from the schematic. And that's the golden standard for how it makes sure that your layout matches with the schematic. Okay, So with that, if you have any questions, feel free to ask your TA, post it on Piazza, or email me at zhl101@ucsd.edu. And with that, let's go to the design and let me give you a quick introduction on how do we do DRC and LVS. So the tool that we're going to use for DRC and LVS is this Pegasus. Very interesting name, right? This is actually not wildly used in industry settings. Typically, for at least our labs tape out, we would prefer to use Calibre, which is from Siemens. As you can see here, there are LVS, PX, Exact, DRC, all these kind of stuff in both Calibre and Pegasus. But here, for this open PDK, which is free, we have to use Pegasus. Just no reason. It's just because what they provided from Skywaters is only compatible with Pegasus so far. Okay, so as you can see here, this is the layout that I made from the last section. This is the inverter V2, I believe. And so the first thing we're going to do is actually, if you just open this layout up, you will probably see some of these circuits or transistors as a black box. It's just going to be like a rectangle with the red marking on it, and you can't see anything inside. You can stick to that because this is the same thing, but if you really want to see what's inside, you can either press E to show the display options, and then you change this display levels from by default 0 when you just started or opened this layout to 32, which is the deepest depth it can get. So this way, it's going to show everything that is inside this P cell, inside this transistor, down to the wells, the diffusions, and everything. Okay, so now let's start the Pegasus. So here, if you click Pegasus and you click Run DRC, this thing is going to show up. So a few things that you need to fill out by yourself is one, this run directory, which I believe you'll need to create a new file for it. So here we have, somewhere that we created for this. Just go in here and just, make sure that you create it in a safe spot, a good spot, and you just name your file DRC. Today is October 14th. Okay. Yes, so this is the first thing that you need to do. And the second thing is that you need to import these rules. So for this rule, you need to import or add this .drc.pvl file, which is located in, so if you go to home, Linux, ing 6, B216 FA 24, and then BNG 216. You go in here. So this is where our PDK is located. Go in here, and then you see this Sky 130 DRC. You go in here, you'll see this .pvl file, which is what you need. So you do add, put this in there, and there you go. Everything is ready here. The rest of the stuff, you can just leave them as blank. And the last thing that you need to do is that in output, or in run data, sorry, it should actually be in run data, you need to turn on this interactive engine. By default, this is not checked. So once you do that, you can start. Okay, so apparently I've done a good job. Hopefully you also did a good job, and there are no DRC errors, meaning that the circuit here that we laid out is indeed manufacturable. So let's deliberately make a mistake, and let's see how Pegasus reacts to it. So if you go in here, let me create a very weird Meta 1. So if I go here, as you probably still remember from the previous session, you go to Meta 1, and you press P, And what I'm gonna do is I'll create this thing, which is very, very close. These two stubs. So if you look at meta 1 only, meta 1 only, this thing has a very short distance, or if we make this mistake even worse, both these two edges are a very short distance. This is only 50 micron. Sorry, 0.05 micron, which is 50 nanometers. This is 60 nanometers, both of which is beyond what I believe this PDK can do. Okay, so let's say, assuming that we have made this mistake, let's run DRC again and see what happens. This is also my first time doing it, so let's take a look together. Yes, as you can see here, it is marked by DRC checking in Pegasus that there seems to be 2 mistakes in Meta 1 layer. So if you press on this, and I believe if you go here, and then you click on, let's see, view by area from layout. What does it do is that it's gonna automatically highlight, as you can see here, down here, this area that the error has been found. Also here. Oh, apparently you don't need to do anything. Just click on it and the error just shows up. Very convenient. Very nice. Okay. And now let's get rid of this thing. Let's create some other weird mistakes that the DRC is going to yell at. So why don't we do something wild, and I'll just copy this transistor and I make it this way. Well, so one thing that you'll notice that is that if you start putting the transistors too close to each other, they're going to actually snap. What I'm saying is that because the source or drain of the previous transistor is shared with the source or drain of the next transistor, and if you move them close enough, they're just going to snap to each other. This is acceptable, by the way. But we're not doing that. We're just going to make a weird mistake. And I'm actually fighting right now with this snapping. I believe there's some way to turn it off. But, well, let's not go there. Okay, yeah. Apparently I won, and this is the very weird thing that we just made. So now the source or drain of these 2 transistors are very close. And actually for this polygon, there are only 45 nanometers of distance. Now let's run Pegasus again and see what it tells us. Okay, so because we copied the transistor, there are more than just, I guess, 2 mistakes. So one is going to show that spacing of M connection to M connection, which is the via, should be larger, right? So here it says this spacing should be larger or greater to 190 nanometers. But then here what we actually have is way less than that, 125 nanometers. That's why it's an error. Same thing here, I guess it's the same mistake. And if we go in here, it's going to say that the spacing of diffusion and diffusion tab to tab or non-abutting diffusion to tab should be 270 nanometers apart. So this was what we just measured. It was like 45 nanometers, which obviously violates this rule. Same thing, I guess, here on the top. Yes, this is tab to tab. This is the body tab. Yeah, so this is written in plain English for you to understand, which is very nice. And if you basically click on this, it's going to light up where the error is happening. Very nice, very convenient. Okay, I believe this should conclude our section on DRC. And let me clear this up. I believe I didn't make any other mistakes on this one. So let's now proceed to LVS, layouts versus schematic. It's also in Pegasus and it's located as here, run LVS. So you see a very similar window pops up, but what you need to do is slightly more than in the DRC's case. So what you need to do is you're gonna go into rules and you need to import the LVS.pvl this time. So you click on add, and if you go to the same directory as before, so this directory, go into the PDK, and you have this Sky 130 LVS folder, and inside there's this .lvs.pvl file that you need to import. So this is the rule file. And then yes, in run data, make sure that you click on interactive engine. I didn't try. If you don't turn it on, what's going to happen? But I suppose you can't probably interact with it, or it's just not that convenient. Same thing here in the run directory. You need to name the file that you wanted to run in, and populate the logs. So here I'll just do it in LVS3, and then let's create another folder here then. So let's call LVS4. And if you go in here, you need to create a new file. Just file name, I'll just name it as file, that's fine. Okay, so this is run set and rules. Now for the input, you have to do a few things. One is that you have to make sure this marking the schematic, which I believe it was by default create CDL, you have to change this to AU CDL. I actually am not sure of what this does, but I believe this is it. When it extracts, it's gonna use the AU CDL view of your schematic to do this checking. And the other thing that you need to do is convert pin to, make sure that you check geometry plus text. And I think by default, it was previously checked at geometry. It's not enough. Okay, what else? Let's take a look. Yeah, run ERC checks. ERC is a subset of LVS or DRC. This is electrical rule check, which also checks if you have any weird, say, connections like parasitic diodes and whatnot in your layout. LVS options, I think this is okay. And now let's do submit. Yes, and you can see that you have a green check here, which is great. Usually for us circuit designers, whenever you see this check, it means you did a perfect job, and you're good to go. At least on the LVS side, I guess. Yeah, so this is definitely the thing that you want to see after hours of working on it. Now let's go into let's also, just as what we did previously, let's now create some deliberate mistakes and see if DRC catches it. So the first thing I'm going to do is I'm just going to move this away from its original connections. So now we have a partially correct layout, but it's definitely not according to the schematic. So now let's run this LVS again. I think for rerunning, you can click on rerun. Okay, as expected, the LVS has errors. And it shows here that the ISL, whatever it is clean. ERC is also empty. Extraction, well, you didn't do it. But the comparison, there are mismatches. So now let's open the report and see. So here it says there are 3 errors. It says short and opens. So this SAO. What is this SAO? I don't believe that they're gonna mark it anywhere because, as I said, for LVS, it assumes that these two guys doesn't know each other's existence at first, right? The schematic doesn't know layout, layout doesn't know schematic. They are individually extracted into a netlist, and the netlists are compared. So that's why, even if there are mismatches, it's only going to tell what it thinks the mismatches are without telling you where they are. So as you can see here, the first mistake or the error here shown is that in layout, there's a pin VDD, and in schematic, there's also a pin VDD. So that's good. That's compared. That's matched. But then this is where the error happens. On the layout, there is this net x03, which if you click on it, it's going to show this guy. So it's going to show that where it's supposed to be in the schematic and where it is in the layout. But then it's actually open, right? Because we don't have any connection up here. So I guess Pegasus is smart enough to know that what the net on this net, this VDD net in the layout view should be matching with the VDD in the schematic, but it's not connected to any pin yet because of the way that we made this mistake. So that's why it's complaining. Same thing for 5, which is this guy, right? And I think the schematic also lights up. So now let's look at this thing, which is the output pin, and you see that it also lights up, but then it's marked as open, right? Because we don't have any connection to it. Finally, this is input, and I guess I can skip that because everything is the same. Okay, now let's correct this mistake and let's make yet another weird mistake. So previously in the layout session, I said or mentioned that in some of the design rules, it is required to have a label and a pin connected on the right net list. So if you don't have this pin, as we previously saw, there will be a LVS error. But what if we don't have the pin? What if we don't have the label? Oh, apparently the labels are gone. So let's try out this. Why don't we delete the pin for now, right? Or actually make this pin, move this pin here, right? So this pin is for input, which should be here right on top, but it's not. So let's see how LVS reacts to that. Rerun. Yes, as expected, there are errors. And what is the error? The error says layout pin. There is a layout pin. There is a schematic pin, but in the layout net here is open, right? So it says, okay, I detected the pins, right? So they are there in your layout, but there is this net in your layout that is open for some reason, which is exactly the error that we created, right? While we move this pin from its original location here, we're leaving this net to be floating, to be open. So let's move this back and rerun. think it's done. Oh yes, it's already done, and because it's correct, there's nothing to be opened, right? I think you can still open them, but it's just going to show a very satisfying green mark as here. Okay, so I think that concludes our session on introduction to DRC and LVS checking. We haven't covered PX, which is very, very important in the entire tape out cycle, but we will cover it in the next session. Take care, good luck, goodbye.